The floor is yours. Thank you so much.
Great, thank you, Karen. You can hear me all right?
Perfectly, yes. You're coming across strong and clear. Thank you.
Okay, let me share my screen. And are you seeing let's see, a full screen version?
Yeah, not quite full. Now it is. Yes, thank you.
It is, okay, great.
Dr. Larson, yes, thank you.
All right, thanks. Yeah, so I wanted to take you through this study that we did. I co-led it, but there were 18 people involved in it, and it took over 2 years to do. And we started it because there was starting to be a lot of discussion about the throwing around the term net zero, and we didn't really have a clear idea of what that actually meant. We know, what it means is that the greenhouse gases emitted to the atmosphere are balanced by the same amount taken out of the atmosphere in a year. But what does that mean in terms of our energy system and our industrial system? And so we decided to do this study to try to make it really vivid what it would mean if we are to get to net zero emissions by 2050 for the United States. So I'm going to go through a bunch of slides. If you have questions that you're losing me, maybe I can answer along the way, but let's try to maybe save most of the questions to the end. So I think we were pretty successful in what we were setting out to do, which is to illustrate to many people what it means to get to net zero. And we ended up attracting a lot of press attention, which helped spread the word around. But we also have given briefings on Capitol Hill and to the executive branch, and a number of private companies have come to us as well. So there's been a really strong interest in this study, and I think you'll begin to see why as I go through some of the results. So the question we were trying to answer, what might the US energy and industrial system look like as we go from where we are today? This is greenhouse gas emissions, and we're at about 6 gigatons, 6 billion tons of CO2 equivalent emitted, and we take that down to zero by 2050. And we did this through a modeling effort. We just drew a straight line from 2020 to 2050 and said, what does our energy system, what is it going to look like if we go along this pathway? We took into consideration non-CO2 emissions, such as those that come from agricultural operations. We also took into account what's called the land sink, which is the absorption of CO2 by trees, by forests, and as well as soils. And we had folks on our team who were experts in those areas who gave us a sense of what we could potentially expect to get done there going out to 2050. And then everything else has to be done by the energy and industrial system. So you see the orange line, that's the system we modeled, going from where it is around 5 gigatons of emissions in 2020 down to a slightly negative emissions by 2050 for the energy and industrial system, to come out with a net zero overall. And I won't go into the details of the models that we use, but this is kind of an overview of the process. So we start on the left-hand side with the demand for what we call energy services. That is the things that we want from energy. We want to be able to travel, vehicle miles traveled. We want to have floor space that we heat or cool. Those sorts of things. It's not the energy per se, it's the service that we want from the energy. And then how much energy is required to deliver those services depends on the technologies that we use to do that. And so that second column there is a model that we call energy pathways, which models the demand side of energy. That is, it specifies the types of vehicles we use to travel our vehicle miles, for example, whether they're electric vehicles or gasoline vehicles and so on. And so when we run that part of the model, we end up with a set of what's called final energy demands that have to be supplied by the energy supply system. And that third column over this RIO supply side cost minimization, that's where we have a model that looks at all of the technology options for supplying the energy that we want. And it chooses the mix that supplies that energy, but also minimizes the cost, subject to different constraints, the most important of which is getting to net zero emissions by 2050. And that then the last step, which I think is probably the most important one that we took, was to take these optimization results, which are at a fairly coarse region, coarse resolution, 14 regions for the entire United States. And we took each of those 14 regions and we did what we call downscaling in various ways to visualize what it means at much more finer resolution, state or sub-state level. And I'll give you some examples of that. And then that lets us assess, sort of what the impacts are on things that matter, like land use, like employment, and like air pollution and health. So that's the modeling framework for our Net Zero America study. And as I said, we had this 14 region macro level model results that we downscaled. And I'm going to talk about these 4 sort of impacts that we've visualized at what we call societally relevant scales. That is, scales that you and I can relate to, I think, pretty easily. So the physical assets and land use, of course, are the starting point, but then what that implies for costs and what the capital requirements are, what it implies for the energy workforce, jobs and labor, as well as air pollution and public health. So I'll run through some results on each of these areas. So starting with and I'll mix the sort of the macro level results with the downscaled results as I go along here. So this is the sort of the highest level macro results. This shows the primary energy, that is the energy that we need in the United States in 2050 under our modeled scenarios. On the left-hand side, I'm showing for comparison what it is today. Basically, this was 2020. Most of our energy comes from fossil fuels and nuclear. If we don't do anything to change the direction very much, we get this reference case in 2050, essentially no new policies, and you don't see too much difference in the energy mix at that point. And then the 5 bars to the right are all pathways that meet the net zero emissions goal by 2050, but they do it in different ways. And the reason we set up 5 different ones is because nobody really knows which direction we're going to end up going in the longer term. But by doing these 5 different ones, we get some sense of what the challenges are and maybe what the opportunities are under different circumstances. So just briefly, I'll describe each of these. The variables that we sort of focused on are the red numbers 1, 2, 3, and 4. Electrification being the first one. So in what we called our E+ scenario, we were very aggressive in how fast we electrified vehicles and buildings. So vehicles meaning converting to electric vehicles from gasoline vehicles, buildings meaning primarily heat pumps for heating and cooling rather than furnaces. And then we had a second case where we didn't electrify as rapidly, but it's still fairly aggressive electrification. And you can see when we don't electrify as rapidly, we need more energy in 2050. And that's because when you electrify, you get an efficiency benefit from that electrification. So you actually need less energy if you electrify more. Biomass is a second parameter that we looked at. Biomass is plant matter. And in 4 of the 5 scenarios, you can see this green section is pretty much the same size on these 4, except for this one in the middle. And in the one in the middle, we allowed the model to use much more biomass if it wanted to use biomass. And in the 4 cases, we limited the amount of biomass that's available to the energy system to no more than what could be provided without changing land use from today. So that means using residues of agricultural production, residues of forestry. We also allowed, in the case of ethanol is a biofuel today that's made from corn in the United States. About 40% of our corn crop is used to make ethanol. We allowed for the possibility in these scenarios that that land could be converted into a more sustainable energy crop, the land still being used for energy, but in a different way. And then in the last two cases here on the right, here's where we sort of pushed and pulled at the amount of solar and wind energy that we could build. In this first case here, the RE minus, we said, let's assume that we can't build too much faster every year than we built in the fastest year previously. So in 2020, that was the record year for construction of solar and wind in the US. We allowed the model to build a little bit faster than that, but not too much faster than that. And then in this case, the RE plus, we said we want the whole energy system to be renewable by 2050. So there you see, and we didn't put any constraints on wind and solar, and you can see wind and solar are the dominant contributors there, along with some biomass. And then the last variable here, carbon capture and storage or use. You can see that in all of our scenarios, the amount of carbon that's captured in 2050 and stored in these four cases is from a billion to almost 2 billion tons per year by 2050. And I'll put that number in context later. Even in this fifth case on the outside here, we said, let's assume we're not allowed to store CO2 underground. We still end up capturing a lot of CO2 in order to take that carbon and recycle it into fuels that we still need within the energy system. It's not an all electric system at that point. So these five pathways, they all meet the same, they all deliver the same energy services, which is what we want ultimately out of energy, but they do it in different ways. And in all five of those, there are what we call 6 pillars of decarbonization that are really essential. All of them are essential if we're going to make the net zero target by 2050. Efficiency and electrification, I mentioned, clean electricity, solar and wind, but also transmission that's needed to bring the solar and the wind from sort of remote places to where it's needed, as well as what it's called firm power that doesn't have emissions. That is, solar and wind are variable, and so you need to be able to balance those through some firm power. Clean fuels, again, a third to half of the final energy in our scenarios is still liquid fuels or gaseous fuels, and we get those through bioenergy, through hydrogen, and through synthetic fuels. I mentioned CO2 capture and utilization, and these last two they're a bit outside of the energy system, but they are essential pillars still, reducing non-CO2 emissions like methane, like N2O, and enhancing land sinks by, for example, growing more trees. So all of these in our models, all of these change at rates that we haven't seen historically. Not that we wouldn't be able to do it, but we have not done it or needed to do it in the past, and that's one of the biggest challenges for this whole transition. So digging a little bit deeper then into these pillars, so electrification and efficiency, you can see this shows the final energy demand by type of fuel in our reference case, where we don't see too much change over time, and then in our two different electrification cases, and you can see we have a dramatic reduction in final energy use, and that if you focus on the E plus case here, you'll see the dark blue, which is electricity, that expands as we go to 2050, while the gasoline and distillate oil that you see, the pink and the sort of the light brownish color here, they decline dramatically, and that's basically electric vehicles replacing internal combustion engine vehicles. So we have more electricity, we have a lot less energy overall, but a bigger fraction of it is electricity. And as I mentioned, a lot of that comes from the transportation sector. Here you can see more dramatically the diesel fuel and gasoline basically go away in this scenario, not as much in the E minus scenario. You see how electricity grows, but you can see that we need a lot less electricity to run our transportation than we did liquid fuels because of the efficiency benefit that comes with electrification. And then you see hydrogen coming in later in this transition, and those are primarily for heavy duty vehicles like trucks. And then we took those, again, those macro results, and we did this downscaling to the state level so that people in different states can get a sense of what the electric vehicle fleet would need to look like in their states if they want to be on track with our net zero pathways. So, you know, by 2030, we have about 17% of our vehicle fleet is electric. It's less than 2% today overall. And then by 2050, we're essentially fully electrified on the light duty vehicles. And then moving over to the second pillar, which is clean electricity. Again, energy overall is decreased, but electricity has gone up substantially by double to quadruple the amount of electricity by 2050, depending on our scenario. The quadrupling being the one where we required the model to use all renewable by 2050. And you can see in all of these cases, solar and wind are very important, regardless of the scenario. The one case where it doesn't grow as rapidly is this RE minus case, where we actually constrained the growth. But in that case, you can see that nuclear becomes a much bigger portion of our electricity supply, as well as natural gas with carbon capture. Those don't appear as significantly in the other scenarios. The electricity generation that I just showed you would require building new solar and wind at the rates that I've shown here. This is gigawatts per year average in each of these 5-year time steps that we investigated. This is how fast we would have to build solar and wind. And over on the right-hand side, I've put in some comparisons. So this is the maximum US rate that we've built in 2020. This is the maximum rate that China has achieved also in 2020, about 120 gigawatts. And then this was the maximum that's been installed in the world in a single year, 238 gigawatts. And without getting into the details here, you can see that these reference, all of our scenarios have growth rates for the US that exceed what we've been done historically. Doesn't mean we can't do it, but we just have to go into it with our eyes wide open. And in this one case where, again, we limited the growth, we don't see as fast a growth, but in that case, this is the same kind of graph, but for the thermal power plants, that is nuclear plants. These are combined cycles with natural gas, with CO2 capture. And I just want to highlight this one scenario here, the RE minus, where we need a lot of new nuclear plants coming into the energy system by 2050. This is in the last decade of this transition. This is on the order of 20 large new nuclear plants every year coming online. Right? So big challenges there. And then taking those, again, those sort of macro results and scaling them down to the level of, in this work, we had a resolution of 4 kilometers. So we figured out where you would not be allowed to build wind and solar. And then we applied an algorithm that located the needed wind and solar in the sort of the least cost places that are allowable. So this is our 2020 map. That's actually, you can see blue is our wind farms that are out there today. Solar is visible a little bit in Southern California, but hard to see because it's not as extensive as wind today. The gray lines are the existing high voltage transmission system. And then we developed this map for each of our scenarios on every 5-year time step. I'm just going to show you a couple of examples. So this is in 2020, we have about 200 gigawatts of wind and solar installed. Jumping to 2030, you can see now the wind is spreading. You're starting to see solar, for example, in the southeast region a bit more coming in, and all of the darker squiggly lines that we've added, those are the additional transmission that we would need in order to bring the wind and solar to demand centers. So by 2030, It's a tripling in the wind and solar capacity, and the transmission grows by about 60%. Those are challenging numbers. And then we go to 2050, and now a lot of the country, driving from say Kansas to New Jersey, you would see a lot of wind turbines. You get out to New Jersey and look offshore, and you would see a lot of offshore wind. In fact, all of the development that's been identified, potential development there is built out in our model. And of course, transmission expands as well. So we have triple the transmission that we have today and 16 times the wind and solar. This is our what we call our E+ scenario, which is sort of a middle of the road scenario. It's not our maximum solar and wind. It's not our minimum solar and wind. Okay, so shifting to the third pillar, which is clean fuels. Again, I mentioned that a third to half of our final energy used in 2050 in our models is still fuel, not electricity. And so we need to have options for fuels. So there are three in the model. We could continue using fossil-derived fuels like gasoline and diesel, and we could offset the emissions that come from that by taking CO2 out of the atmosphere. That's one way of getting carbon neutral fuels. We could make hydrogen from a variety of sources. We have biomass as an option, natural gas with carbon capture, so that we're making the hydrogen without CO2 emissions, or by electrolysis using clean electricity. That's where we split water using electricity that's non-carbon emitting. And we can use hydrogen then directly as a fuel, or we could also blend it into the natural gas system. And then the third option is what we call drop-in hydrocarbon liquid and gaseous fuels. Drop-in meaning that they can directly replace gasoline or diesel. And these we can make from biomass, or we can synthesize them from clean hydrogen and captured CO2. And it turns out that biomass is really important in our modeling. That first graph that I showed you, those green sections, they were all the same in 4 out of the 5 scenarios. That's because the model wants to use all the biomass that's available, because it makes it, the main reason for that is that a lot of the biomass is used with carbon capture and storage. And so when you grow biomass, it takes CO2 out of the atmosphere. You convert that biomass into, say, hydrogen in this particular case, and capture all the CO2 and store it below ground. You've effectively taken CO2 out of the atmosphere and put it underground. And so you get an energy source, hydrogen, that's negative emissions. And that turns out to be really important in getting to this net zero goal. And so this is just showing you the biomass, amount of biomass that's used by the type of technology. So this light blue is biomass into hydrogen. This gray is electricity, but you can see the blue one is really dominating in most of these scenarios. And so we downscaled the bioenergy system to sort of see what that would look like on the ground. And we have a county by county database of biomass availability, which we mapped into 100-mile by 100-mile squares here on the left. These are the sources of biomass: forest residues, crop residues, waste, and then I mentioned corn ethanol land that's converted into more sustainable crops. And the reason we map the resources this way is because biomass is quite expensive to transport very far. And so the assumption is that you're going to use it fairly close to where it's generated. And that's so we in each of these 100-mile square blocks, all the biomass that's available there is going to be used there. And when we convert that into a map of where you would build facilities converting biomass into different types of energy, this is what we come up with by 2050. And you can see that it's sort of a regular grid because of this 100-mile method that we used. But again, most of these are these light green colors, which is biomass to hydrogen with carbon capture and storage. The amount of investment involved in this system over this transition period is close to $1 trillion of capital that basically gets injected into rural America, and it should imply some economic benefits there for those parts of the country. The other thing that I've shown here, these gray areas, these represent the best underground formations in the country for CO2 storage. And since we're capturing CO2 at a lot of facilities, we need to be able to know where that's going to be stored. And so that leads to the fourth pillar, which is to build the CO2 capture and storage system. And this is showing you for the sort of the two extreme scenarios in terms of CO2 capture and storage, the E+ and the RE-, the amount of CO2 each year that we would capture from various sources, with biomass, the green here being, of course, the largest, but also natural gas, the darker gold one in the RE- case. And you can see it starts out, this is the numbers 65 million and 200 million sound like big numbers, but they're relatively modest compared to where we end up with in 2050. So there's rapid growth after 2030 in CO2 capture and storage. CO2 capture and utilization, which is this little red bit here, which is taking CO2 that you've captured and combining it with hydrogen to make fuels. That does play a role in some of our scenarios, not nearly as significant as the geological storage option. And again, so we mapped what the CO2 capture and storage system might look like. So this is a map of where we are today. The gray areas being the storage formations, or the subsurface that's most attractive for storage. These black lines are existing CO2 pipelines. We have quite a significant, 5,000 miles of CO2 pipelines operating in the US today already. And that's for the purposes of CO2 being injected into oil wells to enhance oil production, not for storage per se. But we do have experience with moving CO2 around. So this is 2020. This is 2030. Now, by 2030, we have a few places, you can see these points where we're assuming that you would be capturing some CO2, but we've built out the full pipeline, sort of a national pipeline network. And the reason for that is if we don't have a pipeline network in place, the facilities will be reluctant to invest in capturing their CO2 because they won't have anywhere to send it. So we made the assumption that you would have to build the pipelines in advance of when most of the capture starts. So 2030 capture is just starting. We have the pipeline system, and then by 2050, we have quite an extensive CO2 capture and transportation and storage network across the country. And just to put the number in perspective here, this first bullet point, it's about a billion tons of CO2 per year that's being stored. That's about 1.3 times the current volume of US oil production. So this industry, this CO2 capture and storage industry is on the scale of the current US oil industry by 2050. And in fact, it takes the same sorts of skills and knowledge that oil producers have for how the subsurface works. You're just reversing the process essentially to put carbon back underground. So that industry is going to be important if we're going to be able to, they should be an important player if we're going to be able to build out this CO2 system. All right, so that was running through the sort of the physical assets and land use impacts. Let me go with and not spend quite as much time on it, but just run through these impacts on costs, labor, and air pollution. So in terms of costs, this was a bit of a surprising result for us. This is the total annualized cost for energy, that is capital and operating costs for our entire energy system as a fraction of our gross domestic product going forward. And this is 2020 here. You can see the historical numbers. When in times of crisis, we've seen a much higher percentage of GDP going to energy. But the projections for our scenarios are that we're sort of in line with what it's been historically in times of good economic times. So it looks from this standpoint to be pretty affordable as a transition cost-wise. But the difference is that much more of the cost is capital and much less is operating and fuel. So that means we need to raise capital up front and invest. For example, when we build a wind farm, it costs capital to build the farm, but after that, there's not a lot of operating costs. And so this is a different model of our energy expenditures than what we're accustomed to, and that presents a challenge in itself. We developed this chart for what we projected the spending would need to be in the 2020s, just this decade, and this spending is similar across all of the 5 of our pathways, actually. So the investments that are shown here, if we're on a net zero trajectory, these are going to be pretty secure, investments to be made. A lot of it is in wind and solar, the dark blue, transmission systems, the light blue. On the consumer side, buildings and appliances, heat pumps, and so on, as well as electric vehicles, the darker green here, industry, and some other areas as well. And this particular graph we've shared it with a lot of committees in Congress, and I think they found it very useful in terms of developing proposals for the kinds of government programs that have been proposed for addressing climate change. But overall, it's $2.5 trillion more capital that needs to be mobilized in the 2020s relative to a sort of a no new policy scenario. And then moving over to employment, labor, we developed a model of where jobs would be in different energy sectors over time. So this is each state from 2020 to 2050, and the number of energy supplied jobs in the state. And overall here nationally, there are about 3 million direct energy supply jobs in the 2020s. That's about 500,000 more than in our reference scenario. So this is the E+ scenario. So in aggregate, it's a pretty good story for employment. But if you look carefully at some states, there are losses in jobs. And for example, in West Virginia and Kentucky, where the coal industry goes away very rapidly in our scenarios, because that's the cheapest way to get carbon reductions, as well in Wyoming. Over a longer period, Louisiana loses jobs because oil and gas declines over a longer period than coal. And so if it's places like these states that have the potential to suffer employment losses in this transition, and we'll need to be careful to address those kinds of situations if we're going to be successful with the transition. And then finally, air pollution. We modeled 13 different air pollutant categories. And again, here it's a positive story across the board, I would say. You can see the dramatic reductions in air pollution. And these are criteria air pollutants, not CO2. These are the pollutants that cause health problems. 1/4 to 500,000 premature deaths avoided, valued at between $2 and $4 trillion. So overall, at a macro level, a good story. We also look county by county at what the impacts would be, and we see benefits in every county. The largest coming from the retirement of coal plants and the conversion of motor vehicles from gasoline to electric. This is particularly, even though our automobiles today are relatively clean, because they drive around in urban areas a lot where there's high concentrations of people, there's a lot of exposure that happens, and so it actually has a big impact on health. But by 2050, these basically are removed from the air pollution mix. So just to wrap up then, can the US achieve net zero emissions by 2050? That's a question. We didn't answer that question directly. We just said, what does it look like if we meet if we get to net zero emissions? But I think what our study has shown is that there are pathways to get there, and they do look affordable, but there are some pretty big risks that have to be mitigated, and we have to have policy that's pretty impactful starting now to deal with these risks. So the risks being that we just can't build stuff fast enough, and we can't raise enough capital fast enough to go at the rates that we've shown in the model. And the other is that the big risk is that the social license for the transition is lost or never gained. And for example, if fossil fuel workers are being displaced without something to mitigate that could lead to pushback from large parts of society. So we didn't really address the policy actions that are needed in our study itself, but we did write a commentary in a journal called Joule that sort of in broad brush lays out what we think needs to happen in order to be on a net zero pathway. And then last but not least, we set up a website where you can download our report. It's a 350-page report, so I've skipped over a lot, obviously. But we also have a data explorer there where you can play around with the numbers yourself and dig deeper into the specific areas that you're interested in. And that's it then. Thank you. Happy to take questions. Karen, will you moderate them, or?
I think Madison is looking in the chat, or is Chris looking in the chat, or Maddie, are you?
Yep, I am. It seems like it's just a lot of back and forth with people asking general questions that seem to be answered by other people.
Okay, I see the chat now. I can.
Well, you can certainly see the political ramifications of this too, but I'm skipping over the substance. Well, 2.5 trillion more capital in the 2020s. You said you brought this, you discussed this on Capitol Hill. Oh my.
I did.
I'm sure they had lots of subsequent discussions about that too, as well as discussions during your hearings. What were the, those are energy subcommittees in natural resources and so on. I'm sure where exactly that was discussed.
Yeah, those we briefed. I don't remember the exact names of all the committees, but both in the Senate and the House, the Natural Resources and Science Committee and the we've probably given 100 briefings on Capitol Hill between myself and co-authors.
Wow.
And again, I think the modeling is done in a way that allows people to really begin to put some meat around the bones of what it means to be net zero. And I don't think other models have done as good a job on that. And that's why we got all the attention that we got. But,
yeah, the data explorer function is, I imagine, got a great response from them too. People were able to put in their own, were able to check out how the model works and the different results.
Yeah, we have state fact sheets actually at the website also that take the data out of the Explorer for specific states, which we've briefed folks in state energy agencies and such. I'm seeing one question here. How does your research align with the work of Project Drawdown? Which is, for those of you who aren't familiar with Drawdown, I'm not very familiar with it, but I think it's a project where they estimate what the impact of individual technologies would be on the carbon challenge. And we don't, I imagine some of their technology specific estimates would probably align with, you know, what our model is using but I don't think that, I don't know that Project Drawdown does a sort of a systems level analysis. I think it's very technology by technology. This is we're looking at the entire energy system for the country. And it gets more complicated when you have to look at all of the different energy systems. Ed Sproul says, any consideration of possible development of a plasma as an energy source? That name is familiar, Ed. I think I've met you before. So, yeah, I mean,
I think I sat in on some of your classes, yes.
okay, all right, yeah, you do look a little familiar. Plasma is, you know, one thing that we decided in our modeling to do was to not include technologies that we didn't think had a reasonable chance of being scaled to, you know, significant scale in the time frame up to 2050. And I think plasma fits into that category. You know, it would be great if it were coming along faster, but I don't see that. Okay, I've seen projections about the temperature will hit a 1.5 around 2033. Why is the planning for net zero plan for 2050? Isn't that too late? So if you look at those 1.5 degree scenarios, all of them involve, almost all of them, I think, involve what's called overshoot. So we actually go, we go beyond that warming, but then we draw it back down by taking CO2 out of the atmosphere through this negative emission approach that I mentioned. So yeah, I mean, 1.5 degree, that unfortunately, yeah, 2033 is coming up around the corner. But I don't see that the US or the world for that matter can get there to net zero by 2050 without some kind of overshoot eventually. Family Zoom says, thank you for this work. What do you see as the key organizing factors for the desired trajectory? Government driven, free market driven, grassroots driven? In other words, what are the practical catalysts of this model? For example, economic top down, bottom up, in your opinion? Yeah, I mean, that's a great question. And I think it's going to take all of the above, to quote, you know, somebody who said that a few years back. Government definitely needs to be leading, and that's in our article that I mentioned at the end. We proposed an approach that's really allows for sort of a programmatic approach rather than a project by project approach. So, for example, designating certain regions as sort of renewable energy zones and providing benefits to those regions for encouraging the development of projects, not just one off at a time, but sort of in a more concerted and also participatory manner, where you have all the different stakeholders talking to each other and creating a program that addresses all the diverse you know, viewpoints and concerns that they have, in order to sort of all go forward together, even if it might not be as fast as an individual project would go by itself. If you can do that on a programmatic basis, then maybe we have a chance of going fast enough. But it's, you know, it's a real challenge. I think private capital is going to have to be involved because of the amount of capital that's required. So setting up the policy framework that, you know, properly incentivizes that, but also the regulatory framework that keeps it from going wild, you know, going off in the wrong direction, is also important. So yeah, lots of challenges.
Oh, question. Hello, Eric. Thank you for a great presentation. Reslin here. So you might have missed my presentation. I'm the founder of Footprint to Wings, and our job is to really get the social capital behind movements. And so one of the key things we're interested in is the clarity of the solutions. So Princeton has done an amazing job here, and so excellent information. The only thing is it's really inaccessible. Like, it's hard to understand. Even looking at all the graphs, what we want to do is communicate that information in a much more accessible way. So one of the things we use the gigawatt year as our unit, and then we translate it to like 1 gigawatt year is a nuclear reactor, or 1 gigawatt year is like 30 square miles of solar panels. So from this presentation, I didn't even get a sense of how many gigawatt years we would need. I mean, I think it's like 1700, I don't know. But that's one thing we want to do. And then we want to map it out in states. And then we want to get people in those states to champion the energy thing in their neighborhoods, right? So another metric we've come up with is the NIMBY coefficient. So try to like figure out which has a higher NIMBY coefficient at the end of the day. And we feel it's important to front load this conversation. So my question would be, are you working on like usability or user friendliness of this, or is this a document you've written just for other experts? That would be one thing.
Yeah, I mean, I think it sounds like if you guys could take our report and translate it into the terms that you're working with, would be a great project. We actually thought we were being much more communicative than the average academic. So, which is why I think we got a lot of attention. But in terms of the metrics that you're talking about, we haven't, we set up the website to let people take their time and go through the data. I'm sure you could figure out how to translate it into gigawatt years easily enough.
I had troubles. I would need to sit. It was this huge spreadsheet. I'm like, where is this?
But I'd be happy to spend an hour with you to try to figure out how to do it, because I don't think it'll be that difficult. And if you think that's an effective way to communicate sort of societally, I think we need to try everything.
Okay, I'll take you up on it.
Yeah.
I wasn't even aware that about these CO2 pipelines. That looks pretty essential for the success of this transformation. And can you tell us a bit more about the CO2 pipelines?
Yeah, so I mean, CO2 pipelines today, I mentioned there's 5,000 miles of them, and what they're used for is they actually take CO2 out of the ground. There are pockets of natural CO2, and they actually mine the CO2, put it in the pipeline, and send it down to the oil fields in West Texas primarily, where it's injected into the oil fields. It pushes more oil out, and then the CO2 eventually over time it's going to stay below ground. So it will, over time, it'll end up being stored, put back below ground. But the CO2 pipelines they're underground pipelines. They probably look like natural gas pipelines, maybe a little bit smaller. But yeah, it's been going on for 15, 20 years at least. But building out a network like what we proposed, of course, that's a different challenge. And again, the government backed the natural gas pipeline build out, right? Which helped us to get to where we are today with, what we enjoy with natural gas in our energy system. If it were possible for the government to backstop the building of the pipelines, again, we need those pipelines there before we're going to get a lot of people capturing CO2 to put into them. So it's a bit of a chicken and egg kind of issue.
All complex.
Yeah.
Did you have different reactions to the different pillars of decarbonization when you were talking about this on Capitol Hill?
Just everybody has their favorite pillar, and everybody has the pillar that they hate. CO2 storage is one that's not popular with a lot of people. Everybody loves wind and solar. You know, the point we try to make is that we're going to need everything if we're going to get this done, and so we have to sort of check our biases a bit at the door and figure out, you know, what's the right mix here to go forward. And there's going to be some compromise that is involved in that process. But you know, that's the potential downside of not getting this done is big enough, I think, that it's cause to get together on it.
Yeah, the West Virginia and Kentucky dilemma is something that it certainly needs to be addressed. How much of the legislative proposals have really gone into addressing these pillars of decarbonization up to now? I don't know if you could give us.
You know, I'm not familiar with all of the details of the Build Back Better plan that was proposed. The original one was $3.5 trillion of government spending, and not all of that on climate related, but it was a step in the, you know, headed in the right direction compared to the $2.5 trillion number that I put out. So I think the way Biden is going about it in the government is every department in the government has somebody who's worrying about climate change issues. And so it is a whole of government approach, which again, I think is essential to, if we're gonna address this issue. And, you know, coming back to the West Virginia, you see what Joe mentioned, you know, how he looks at this legislation. He's looking out for his constituencies to a certain extent. But on the other hand, some of you may have heard that the president of I think it's the coal miners union in West Virginia, basically wrote a letter to Manchin and said, you know, you should support this legislation because in the legislation there is support for transitioning workers out of the coal, and coal is going away regardless of whether we do anything about climate or not, just for economic reasons. And so there's a recognition that and so I guess in the bill there were some provisions for mitigating the harms that might come from job losses.
Oh, that's fascinating. I hadn't heard of that. I think there were some questions in the chat that were coming.
Yep, there's 2 questions in the chat.
And we have just a couple more minutes. Yeah, so that's really important. Go ahead, please.
All right, real quick. One of the charts mentions coal coke. Is there any consideration of alternative reduction of iron ore rather than? Yeah, so in our model, we decarbonized iron and steel by using direct reduction of iron, which uses hydrogen as a reductant and an energy source and gets rid of the blast furnaces. And any thoughts on how the $1 trillion of the infrastructure bill should be spent while rebuilding bridges? You know, any of the ways that support the transition, the pathways that I've laid out, I would be supportive of, but I don't have any specific sort of suggestions at this point.
Are there any other questions, Madison, that you want to bring up?
I don't think so.
Well, you've certainly given us an enormous amount to think about, and looking at your report and Jewel, I guess the article you said was in JOULE, Jewel magazine?
Yeah.
Or journal?
Yeah.
It gives us a beginning place to look at the research that you've done and to get a better understanding of these extraordinary challenges. We couldn't be any luckier than to have somebody who has your depth of knowledge and experience to share this with us. And we're certainly grateful for all your work.
Happy to be here. And if you go to the website for the Net Zero America, you can get to the Jewel article and other things as well there. And, you know, feel free to reach out. My email is there somewhere probably. and be happy to engage further.
Wonderful. Thank you so much. We're
Okay.
very grateful.
Yeah.
Thank you.
Bye-bye.
Fabulous. Amazing presentation. Did anybody, we can stop the recording, please, and then we.
Faster.
Okay, let me make a very quick introduction because we want the